Every photo you take, every email you send, every video you stream, it all demands physical space. And we are rapidly approaching a threshold where the world produces more information than we can actually build containers to hold. By 2025, driven by the explosion of 4K streaming, continuous updates from smart devices, and the massive datasets required to train artificial intelligence, global data generation is projected to hit 175 zettabytes. To put that scale in perspective, a single zettabyte is 1 trillion gigabytes. Keeping all this information alive requires massive warehouse-sized data centers. These facilities already consume roughly 2% of the total global power supply, placing an enormous and growing strain on the world's energy grids just to keep the servers cool and running. Our current storage methods are not scaling to match this volume. Based on these projections, the industry is on track to face a significant shortfall between the data we create and our physical ability to preserve it. For decades, the semiconductor industry kept pace by simply shrinking transistors so more memory could fit onto a single chip. But that strategy has hit a physical wall known as the silicon ceiling. When you shrink a flash memory cell down to 10 nanometers, you collide with the limits of quantum mechanics. At this tiny scale, the Heisenberg uncertainty principle takes over. You can no longer reliably contain electrons, and the data leaks right out of the hardware. Compounding this quantum limit is a severe material shortage. Based on current growth curves, the global demand for memory storage is projected to outstrip the entire world's supply of wafer-grade silicon within a few decades. We aren't just running out of warehouse space for servers, we are running out of the raw atoms required to manufacture hard drives. The solution exists outside the realm of microelectronics. Nature solved the data density problem 3.8 billion years ago with a biological polymer, DNA. A modern solid-state drive can pack 1 bit of data into 10 nanometers of space. A DNA molecule, however, stores 2 bits of information along just 0.34 nanometers of its backbone. This chart visualizes that density gap. Standard media like flash drives and magnetic tape cluster near the middle, dwarfed by DNA, which holds up to 200 petabytes in a single gram. At that density, you could take all the digital data that currently exists on Earth and fit it into a single shoebox filled with tens of kilograms of DNA. To use biology as storage, binary files are translated into base 3 codes and mapped to the 4 chemical letters of DNA. Then, data is split into fragments, and engineers append indexing and error correction codes to ensure files are reassembled without loss. Once the code is mapped out, the data moves to the write phase. Instead of using a magnetic head to alter charges on a metal platter, lab equipment chemically synthesizes actual physical molecules, building the requested DNA strands letter by letter. This graph tracks how different storage mediums retain data across temperatures. Notice the dark blue line at the bottom representing flash memory, which degrades rapidly. Compare that to the red lines showing DNA's chemical breakdown, proving it remains intact for millennia. We know this works outside of a laboratory simulation. Researchers have sequenced intact genomes of extinct species, like this baby mammoth, reading genetic data stored in permafrost for hundreds of thousands of years. By converting digital files into biological molecules, we bypass the short lifespan of electronic hardware. It creates an archival medium that requires zero electricity to survive for centuries. While the science is proven, mass commercial adoption is currently blocked by a major engineering bottleneck: write-read latency. When you click a file on your computer, a solid-state drive retrieves it in microseconds. Synthesizing new DNA sequences and then running them through a sequencer to read them back takes anywhere from a few hours to 2 full days. That delay forces us to separate our information based on how quickly we need it. Fast-moving, hot data, like your texts, emails, and social media feeds, will stay on silicone chips built for speed. But cold data, like medical records, legal archives, and historical documents, can be dropped into biological storage. A biological hard drive isn't going to make your smartphone run any faster. What it offers is a stable, long-term solution for human knowledge, capable of preserving records for centuries or more. To shrink that latency gap, groups like Microsoft Research and the government's MIST program are pioneering enzymatic synthesis. By engineering biological enzymes to construct DNA instead of relying on older chemical methods, they are reducing the time it takes to write files. And for reading those files, nanopore technology is replacing bulky laboratory equipment. By physically threading single molecular chains through microscopic protein pores, these systems can sequence and retrieve data with far less overhead than previous methods. As these reading and writing tools mature, they will unlock a carbon-neutral computing ecosystem where our digital footprint is compact, energy efficient, and resistant to the decay of time. We didn't have to invent a new storage medium from scratch. We just finally learned how to read the one nature already perfected. If you want to keep exploring the mechanics of our digital world, hit subscribe